Yes, Renu ma'am.
Yeah, yes, sir.
Yes, ma'am.
Yes,
Please start.
now you can start session.
Okay. Good morning, all participants, organizing member, and keynote speaker. I, Dr. Renu Nandal, from the Department of Computer Science and Engineering, University Institute of Engineering and Technology, Maharishi Dayanand University, Rohtak. Welcome to all in the fourth session of All India Council of Technical Education. AICT Training and Learning sponsored faculty development program on 3D printing and design. I am happy to introduce Dr. Ankush Raina, who is going to talk about the tribiological application of 3D printed parts. Dr. Ankush has a vast experience in teaching and in the field of 3D printing technology. He obtained PhD degree from Sri Mata Vaishno Devi University, Katra. He published a large number of articles in the SCI and Scopus Index journal having H index 11, I10 index 13, and citation 375. He is working as assistant professor in the School of Mechanical Engineering at Mata Vaishno Devi University, Katra. I request all the participants to keep their audio and camera off. If you have any query, put them in the chat box only. We will discuss all the doubts at the end of the session. Now, I welcome Dr. Ankush to continue the session and share his precious knowledge. So,
I thank you, Dr. Renu, for this wonderful
thank you very much.
introduction. Uh, Actually, I think I will not be visible to you because my camera will not work. I am on 2G network right now. But I think I'm audible to you.
Yeah, you are audible, sir. Clearly audible.
Okay, so first of all, I'll thank all the organizers, Dr. Deepak especially. So now I will share my screen with you. I think the screen is visible.
Yes, sir.
Yeah, it's
Okay, okay. So I'll start presentation. I think you can see the full screen now.
Yes, sir. It's visible.
Okay. So good morning, everyone. I will talk about the tribological applications of 3D printed parts. Because whenever we talk about 3D printing and its applications, so there are certain areas where tribology plays an important role. So I will be talking about that aspect also, and basics of the 3D printing might have already been covered by different speakers in this talk, but I will try to correlate the tribology with 3D printed parts. So first part of the slide of this presentation will be regarding 3D printing, and second part I will try to talk about some tribology and then some research work which has already been done by me and my group. So this is a disclaimer statement, and contents of the presentation will be, first of all, I'll talk about additive manufacturing, then 3D printing, types of 3D printing, 3D printing materials, then tribology, then application areas of tribology, then what is the relation between tribology and 3D printing, then tribological behavior of FDM-based polymer nanocomposites, a study which has already been done by my group, then surface engineering of FDM-based 3D printed parts, then study of FDM-based impellers. So talking about additive manufacturing, the nature has given us so many lessons, and from the nature we have learned additive manufacturing also. So here from the images you can see how the nest is being built up by the birds. So layer by layer method is being used, and similarly if we take into consideration other example, it's an example of a porter wasp rather. Porter wasp tries to build up its nest again layer by layer. So we can say it is additive manufacturing, and it is a technology basically which is used to build the objects by adding the layers on different layer by layer method, and whether it may be your plastic material, it may be your metal, it may be your concrete. So you can use different types of materials by using this technology, and you can additive manufacture those components which are required to you. So basically, if you talk about the additive manufacturing, it is it comprises of different aspects such as your rapid prototyping, digital manufacturing, layered manufacturing, and additive fabrication, and most importantly your 3D printing. So it has different applications which we'll be discussing in the coming slides. There are some advantages which also we'll talk about, and certainly there are some disadvantages, or you can say some limitations of this technology that we will also talk about in the coming slides. So first of all, the difference between the additive and subtractive manufacturing, it's quite basic and common thing. Additive manufacturing, or AM, is basically suitably named to describe the technology that is used to build the 3D objects by adding materials layer by layer. The term additive basically is used to denote over here that we are using a method of adding and building up the product repeatedly. So, but in comparison to additive manufacturing, if we talk about your subtractive manufacturing is an opposite method of this additive manufacturing. It manufactures the objects, and basically by subtracting, by using different machining operations. It can be milling, it can be drilling, or it can be any other cutting operation. It is also called as a traditional manufacturing, which basically we are aware of, and is used by means of your CNC machining. So additive manufacturing to add something, and subtractive manufacturing to subtract a material from the already manufactured component. So why it is important to discuss additive manufacturing, why this method has advantages over the subtractive manufacturing. The first figure here you can see is that the first one here you can see that we can manufacture the materials with different properties. So you can see that in the topmost layer of this image is 90% ceramic and 10% bond coat, and certainly you can functionalize the material as per your choice by using the different coating and different layers of different materials. So we can generate some functional materials as per our requirement. You can see the bone over here. In that you might be aware of that the strength of the bone at the central part is more in comparison to the joints, whereas at the joints the porosity is more. So if you want to replicate some sort of bone-like structure, so the material should be selected, or it should be designed, or it should be manufactured in such a way that it gives uh, the similar properties as the human bone or as any other bone gives. So additive manufacturing basically helps us to design or to fabricate such kind of structures. So the most important aspect is your part complexity. We can, generate, or we can produce the parts with the complex nature, which are not easily possible with the other or the conventional methods. Secondly, the speed is also an important aspect of your additive manufacturing. Also, we have the choice of material selection. We can select the materials based upon the applications, but there are limitations that we will be discussing regarding the material selection in the coming slides. We can also customize the number of parts, how many number of parts uh, we want to produce. We have just to give you just have to give up a program file to that, and you can then customize when you want to produce 10 parts, 20 parts. We can have that flexibility over here also. And cost obviously is an important factor in additive manufacturing, which is less in comparison to the other ones, because the wastage in your additive manufacturing is negligible, or it is very it is less, whereas in case of your comparing your subtractive manufacturing, the wastages are there, because almost more than 50% of the material is removed, and we are left with less than that material. So wastage is always involved, and if the wastage of the material will be there, certainly it will add to the cost of the final product. So talking about 3D printing, basic definition. Despite 3D printing being nearly synonymous with rapid prototyping, there are the scenarios where it's again a viable production process. So typically, 3D printing is used in different sectors, which includes transportation, healthcare, military, and education. And these applications involve basically low volumes and complex geometries, as discussed in the previous slide, that we can have the choice to produce the geometries which are complex in nature, and we can produce those geometries very easily in comparison to the other conventional processes. Often the most important application is your aerospace and medical applications nowadays. And there are wide variety of applications in this aerospace industry and in medical applications. And the materials which are used in 3D printing, these includes resins, plastics, and in some cases we are using metals also. So here you can also see that in 3D printing, 25% of the contribution of the 3D printing is for prototyping, 16% is for product development, and 11% is for innovation and design, and 99% is for reduction of the cost, and 10% is increasing the overall efficiency of your systems. So again, it is used to build the concept models, functional prototypes, factory toolings, and even finished goods. So before we move ahead, it is important to understand the prototypes, what a prototype is. So we have different types of prototypes which are basically used. The first one is a design prototype. Secondly, we have a geometric prototype, then functional prototype, then technical prototype, and industrial prototyping. So talking about the design prototype, I'll quickly go through that. This type of a prototype is constructed to test whether the realized object meets the optical requirements or fits to the overall concept, whether there is any clearance, or whether there is any other tolerance. So we basically use this design prototype to find out that. So basically these models have no functionality and can only be manufactured of a standard plastics. So these are just to use to meet the design requirements. Then geometrical prototype is the one which has the exact dimensions of the application and can be installed to see whether other modifications are required or not, whether there is a change in the dimensions of your prototype is required or not. So this is basically a geometric prototype. Then coming towards the functional prototype, which is an important prototype, it basically maps the functionalities of the planned component and can be tested directly in the application. So for these, it is always recommended that a small series of sample parts to be manufactured, so that they can be tested under various conditions. So basically, this functional prototype, is the main or the backbone of your all these prototypes. Then coming towards a technical prototype. So if we talk about technical prototype, then if the final geometry and the material have been decided, because that has been decided in the previous prototypes have been decided, then what happens is that the finished application is tested with the technical prototype. So what we use is the model basically in this case is already complete. It matches the final product with respect to material, behavior, and geometry. Only we are trying to test its technicality. So that's what for the technical prototype is used. So after that, the last one is your industrial prototyping. Before the product goes for a mass production, what we do is we produce a small series of prototypes, and this small series of prototypes are basically used in the automotive industries particularly, and are given to the customers, or so that they can check whether this prototype which we have produced is working properly or not, and if there is any possibility of some modification or some change or in the design, that can be taken into consideration. So these are the different types of the prototypes which are important when we talk about 3D printing technology. So these are basically again the 3D printing techniques. Again, this is a basic part which has already been, which might have already been covered. So I will quickly again go through all these points. So these are the different 3D printing techniques which we use, uh, right from stereolithography to electron beam melting. So I'll quickly talk about all these. Stereolithography, is an original industrial 3D printing process, and also denoted by SLA. This SLA printers produces the parts with high level of detail, smooth surface finish, and exact tolerances. It's widely used in medical industry, and common applications includes your anatomical models and microfluidics. Then coming towards the selective laser sintering, SLS. In this, the nylon based powders are melted into solid plastics, and since the SLS parts are made from metal thermoplastic materials, so they are durable, suitable for functional testing, and can support living hinges and sharp fits. So in comparison to the previous process, the parts are stronger and have the rougher surface finishes. Talking about FDM, I'll talk about FDM in the coming slide, because whatever the work we have done is basically on the FDM. So I'll talk about FDM in the next slide. So coming towards polyjet, polyjet can fabricate the parts with multiple properties such as colors and different materials. So if the design is single or rigid plastic, it is always recommended to go with the stereolithography or SLS, the above two processes, because it is more economical. Then coming towards the digital light process, digital light processing is similar to SLA in that it cures liquid resin using light. In that case, light is basically used for producing the parts. The primary difference between the two categories is that the digital light processing uses a digital light projector screen, whereas SLA uses a UV laser. So coming towards the next, that is multi-jet fusion. If you talk about SLS, it is similar to SLS. So, but it also builds the functional parts from nylon powder. In that case, rather than using the laser to sinter the powder, this MJF or multi-jet fusion uses an inkjet array to apply fusing agents to the bed of the nylon powder. Then direct metal laser sintering. Basically, this technology is used to print the metal parts. So metal 3D printing is done by this process. So it is often used to reduce the metal multiple part assemblies into a single component or lightweight parts with internal channels or hollowed features. Similarly, the coming towards the next, that is your electron beam melting. This is another metal 3D printing technology that uses an electron beam that is controlled by electromagnetic coils to melt the metal powder. The printing bed is heated up and in a vacuum condition during the build. So basically, these are all the 3D printing technologies which are there. A lot of data is available about these techniques. These are basic techniques. So coming towards the FDM, because a lot of work has been done by using this technology and this technique, and we have also performed the studies using this technology only, FDM technology. So in that case, a continuous filament of thermoplastic polymer is used to 3D print the layers of the materials. The filament basically is heated at the nozzle to reach a semi-liquid state, and then extruded on the platform or on the top of the previously printed layer. So the thermoplasticity of this polymer filament is the important property in this method, which allows the filaments to fuse together, because a fusion of the filaments is an important aspect, because it governs the various properties and the various characteristics of the finished product. The layer thickness, the width, and the orientation of the filaments, and the air gaps basically are the main processing parameters, as I told you, because these will affect the different properties of the 3D printed parts. So the low cost and high speed and simplicity of the process are the main benefits. That's why the FDM is widely used in printing at polymer parts. So this one will give you an idea about the 3D printing materials which are being used. All the materials are used, but different materials have different properties. So based upon that, a figure has been made over here. We have the 3D printing materials. If we talk about the plastics, we have different categories in that, and most of the work has been done on the plastics only. So coming towards the ceramics and organic materials, we have different materials in that case also. These nowadays, this this ceramic and organic materials category is being widely explored, and also you can see that the metals are being also explored to meet the requirements. So, but talking about the plastics, there are a lot of a lot of work has already been done, but you know that plastic materials cannot fulfill all the requirements and cannot be used in all the application areas. That's why the other options, that is your ceramics and organic materials and your metals, have also been explored. But these are the wide variety of materials which are being used. But I can say that there is a lot of work which is further required to be done in order to explore all these properties and all these functionalities of all these materials. Uh, I think I'm audible.
Yes, sir, you are audible.
Okay. So,
thank you.
So coming towards the challenges and shortcomings of this technology. Uh, Challenges, the most important is your fiber orientation, because fiber orientation plays an important role in governing the properties of these different materials, which are, which is the final product. So there is a challenge to find out what kind of a fiber orientation will be there, which will give us which will give us the best results. So again, it is a challenge, but a challenge can always, be met if you look into that from different perspectives. And then if you come towards the next challenge, that is your bonding between the fiber and the matrix. As I told you, that the temperature plays an important role. That if the bonding between the fiber and the matrix will be good, certainly the properties of the finished product will be good. So again, it is a challenge to produce a material or produce a finished product with good bonding. Then void formation, again, it is there, which is again a challenge. Then cost of the system equipment, because you know that we have different 3D printing technologies, and we have the different techniques for this 3D printing. So each and every technique has its constraints. So it's again a challenge to look into the cost of the equipments which are being used to print these parts. Then cost of the material, because depending upon your applications, the material is selected, and this this cost of the material plays an important role in order to decide the final cost of the product. Then finished quality of the product, again, is a challenge. Then material selection is again a challenge, uh, which is an important factor when you look into the material selection point of view. If you have selected a material which is not fulfilling your requirements when you're using it for some application, so again the whole job and whole the work will uh, go in vain. So it's an important aspect that how you will select your material, what kind of a material, or what kind of the functional materials which will have the different layers and which will have the different properties, how you will uh, look into that aspect. That again is a challenge in this technology. Shortcomings obviously are the weak mechanical properties, particularly if we talk about the polymer printed parts. Then interlayer strength. Then again, the pore surface quality, these are the shortcomings. Limited number of thermoplastic materials are there, if we talk about that. Then high energy consumption and copyright infringements are some of the shortcomings of this technology. But hopefully with the passage of time and with the recent advancements, these challenges and shortcomings will definitely be overcome. And this 3D printing technology, as you know, it's growing vastly, and it will find uh, much more applications in comparison to if you compare it with today itself. So the considerations, if we talk about when we go for 3D printing or when we'll go for the conventional processes of your this material fabrication. So if we talk about what are the basic factors on which should be considered while selecting the 3D printing process, that these are the budget requirements. This is your functional requirement, cosmetic appearance, obviously the shape or the aesthetic looks of the material should be met if you're talking about that. Then geometry is an important aspect, and again material selection, as I'm talking about that, which is again an important aspect, because material selection plays an important role regarding the applicability of your products. So coming towards the next slide, now I will. These were the basics regarding your 3D printing, which you will be which you are aware of, might be discussed in the previous talk by Dr. Abid Ali. But this is tribology, which is something new in this course. So tribology, basically, it was first of all reported by Peter Jost. It is a science which concerned to the friction, wear, and lubrication mechanism. So since sorry, since you if you are all from the mechanical background, so you might be aware of this term tribology. So the performance, reliability, and efficiency of the system basically depends upon the friction and wear characteristics of a particular component. So the widespread involvement of wear and friction, you know that everywhere the friction is there, and in order to overcome the friction, there is always a wastage of energy, and material wastage is always there. So friction and wear basically, uh, is an important aspect when you talk about tribology. Whenever you talk about the motion of some components or some sliding surfaces, so the goal of the tribologists is always to reduce those energy losses by bringing the improvements in different aspects. So there are reports which have projected that if we'll use best tribological practices, we can save the GDP or GNP, gross national product, of an industrialized nation by 1 to 1.4%. That will contribute to the economy, and which will give boost to the economy. But the use of the best tribological practices are required. So if you take into consideration in this figure, you can see that in automobile sector only 35% of energy is being wasted by friction and wear itself. And if you talk about light trucks and other trucks, the percentages are given. So you can say that the most of the energy is being wasted in automobiles, light trucks, and other trucks. So this gives us an insight. If we look into the performance of the materials or performance of these the components which are used in automobiles, light trucks, and other trucks, from the tribological point of view, surely we can reduce the energy wastes, or we can improve the savings, and certainly it will help to improve the economy of a particular nation. So tribology basically deals with the friction, wear, and lubrication in order to improve the performance, reliability, and efficiency of the mechanical components. So there are different areas of the tribology, application areas of the tribology. So first, when the tribology was introduced, although friction, is a term which is being used since ages, but the concept and the term of tribology was coined in 1966 which encompasses of friction, wear, and lubrication. So when it was started, this term was coined. So they were, the Peter Jost was talking about industrial tribology only, because most of the frictional and the wear losses are, due to the industries, different mechanical components, different machines. These are basically due to the industries. So industrial tribology was, first of all, basically coined in 1966. But with the passage of time, ocean tribology was coined. Then manufacturing tribology was segregated therefrom. Then we came to know about the important aspect, that is biotribology, because if we talk about the biological systems, there is also some tribology. There is also some friction, wear, and lubrication mechanisms. So if you talk about ocean tribology, it involves the investigation of friction and wear in a seawater environment. And the seawater, is very corrosive in nature, and it results in the increase in the surface roughness. And if the surface roughness is increasing, it certainly means that when the components will slide, there will be a lot of wear and a lot of friction. Because you know that if you are moving on a rough surface, if the surface is rough in comparison to a smooth surface, your energy requirements will be more, if you're talking about the sliding applications, or if you're talking about the rolling applications. So what happens is that in ocean tribology, the corrosive nature of the material, the seawater, it tries to do, it tries to increase the surface roughness. Ultimately what happens is that it corrodes the parts, and generally the energy requirements will be more, and certainly the material wastage will be more. So wear and tear of the material will be more. So tribological studies on different materials has been carried out. If we talk about the ocean tribology, these includes, polymers, metals, alloys, and different composites. So in ocean tribology, we are also working, and we are also looking into the different aspects of the materials. And why I'm talking about tribology over here, because we can say that we can also use the 3D printed parts in your marine applications or in your ocean technologies. We can use there. So that's why I'm talking about tribology in 3D printing. So coming towards the next important aspect, that is your manufacturing tribology. It is basically, when we manufacture the materials, it includes the study of metalworking fluids employed in machining operations. The metalworking fluids are used in various machining operations, your conventional machining operations, turning, milling, grinding, and drilling. Then coming towards the biotribology, this was basically coined or introduced by Dawson and Wright to highlight the importance of the tribology in your biological systems. In that we have the oral tribology, ocular tribology, tribology of natural synovial joints and artificial replacements, and cardiovascular tribology. So now talking about oral tribology, it involves the study of wear of dentures. You are aware of that, as the age of a person, or a person grows older, there is a possible need of partial or complete dentures, because your teeth are, that got worn out. So due to which, there is a replacement of that. There is always a requirement to replace that, your crowns or your teeth cappings. So these are to be replaced. So in order to develop those durable dentures, one must have the knowledge of wear of teeth and the effect of materials on the teeth. So where the 3D printing then comes in, the 3D printing comes in dentistry also, wherein you have to select the particular material, you have to 3D print that material, and you have to replace the old dentures. So that's what oral tribology is all about. So coming towards the next, then is ocular tribology. It deals with the lubrication of contact lenses. There is a continuous movement of eyelids, that over the cornea, which leads to the wear of the contact lenses. So here also the tribology plays an important role. Then coming towards the synovial joints and the artificial replacements, you might have observed that the synovial joints are the movable joints, and a synovial fluid is present in between these joints, which acts as a lubricant and reduces the wear and friction of your synovial joints. So the tribological study of the joints will help us in choosing the right material. In fact, we have the knee cappings and all that. We can also 3D print, but the fact of the matter is that you must select, or you must have the right material for that particular application. If the material will be, will wear out over there, the debris will not go out. if you talk about a common machining operation, the material is getting removed over there from the wear. Debris will go here and there, and it will be collected, it will go into the environment. But whenever you're talking about the synovial joints, if there is a wear of the material within your leg or within your joint, what will happen? The wear particles will remain there, they will not come out, and those wear particles will, what will they will do, they will have an adverse effect, or they will they can also produce carcinogenic effects on human body. So it is very important to understand the tribology over there, natural synovial joints tribology. So it is very important to understand from the material selection point of view whether you have selected a good material or not. So if you are using the 3D printer, you can use the 3D printing technology to produce those knee cappings and all that. But the fact remains the same, that the material should not wear out, as it will have an adverse effect on the human life. So coming towards the next, that is your cardiovascular tribology. Artificial heart valves are implanted in the patients who have the damaged their heart valves. So basically there are two types of valves which are used, mechanical heart valves and bioprosthetic heart valves. So we can also use the 3D printing technology to for this purpose also. And again, the tribology is also involved over there, because there is always friction and wear that is involved therein. So you can see now the scope of a tribology over there in as well as in 3D printing. So coming towards the types of wear, if you talk about wear, so I will quickly go through these aspects. That is your adhesive wear. Adhesive wear basically is if two material surfaces or metal surfaces are in contact or in sliding contact, the metal of the softer surface will be transferred to the other material, and basically this is due to the mutual affinity between the materials. So it will be more when the loads will be high and the temperature and pressures will be high, because there will be an asperity to asperity contact. Asperity basically we call as, if we take into consideration a surface profile, you will see there are peaks and there are valleys. The peaks are basically called as asperities. Those peaks will come in contact with the other surface. So those peaks will come in contact, and they will be damaged and will be transferred to the other material. So that is basically called as an adhesive wear. Similarly, we have an abrasive wear. Abrasive wear is somewhat different from the adhesive wear. Abrasive, in case of abrasive wear, there will always be an abrasion or there will be a cutting action. What happens is that the hard particle rolls under the pressure. It tries to scratch the surface away. So I'll show some images about this adhesive and abrasive wear. So basically, this adhesive wear is different from adhesive wear. Then coming towards the corrosive wear will be due to due to the chemical reaction between the material and the corroding medium, which can be either due to chemical reagent or the reactive lubricant, or it is generally predominant in case of your, as I told you, in case of the marine environments where where there is corrosive environment is there. Then comes towards the erosive wear. Erosive wear, what is erosion? So from that the erosive wear term has been coined. So this erosive wear basically, the common example I'll tell you regarding the pumps, or the impellers in the pumps or turbine blades. What happens is that when a fluid coming with a high velocity and it encompasses of some solid particles, when they hit with a high velocity to a particular surface, they produce some erosion. So that is called as an erosive wear. Okay. Then coming towards the fatigue wear, again, what is a fatigue? Fatigue wear is a type of wear where a number of cycles are needed to generate the debris. So contact between the asperities with very high local stress are repeated. What happens is that due to which wear occurs between the different components due to sliding or due to rolling. So these are basically the different types of wears we have. Talking about now, if we have the friction, if we have the wear, so what will be done to reduce that? How that can be reduced? So certainly that the lubrication is one of the oldest method to reduce friction and wear. The basic function of a lubricant is that it basically separates the contacting surfaces. When there will be no contact between the surfaces, there will be minimum friction and there will be minimum wear. So the function of a lubricant, is to lubricate or to reduce the friction. It's the prime function. Secondly, it helps in the cooling, it helps in cleaning, it helps in reducing the noise, it helps in protection, or it helps in reducing the wear. So if we talk about the friction, the function of a lubricant is to reduce the friction. If we talk about the friction, so the effects of friction are what? Why we are reducing this friction? Because this friction will cause a metal to metal contact, and if there will be metal to metal contact, there will be wear and there will be high friction, and due to which there will be high energy requirements. Secondly, the friction causes wear and tear. Thirdly, it has, the capability to generate heat. You know that due to friction the heat will be generated, and obviously when the heat will be generated, it will go into the environment and it will add on to the energy losses. Then certainly, if you have the friction, if you have the resistance, there will be more power which will be required to that in sliding or in rolling. So certainly there will be more power loss. So nowadays, what we do is we talk about nanotechnology, and the nanomaterials are being used to improve the lubrication characteristics, to improve the friction characteristics, and to improve the wear characteristics. So there are different influencing parameters when we talk about nanotechnology, which governs the overall functioning of your tribological components, the tribological properties. So what are those factors? The surface roughness. Surface roughness is an important aspect. You can see over here, we have the different nanoparticles that are being used. And if in the first image, you can see the surface roughness, is more. And in the second image, you can see that the surface roughness is less, although it has also a relation with the particles. So you can see if the surface is smooth, there will be less friction. But in the first image, you can see there are the particles which are embedding in the surface, and certainly that also plays an important role in order to govern the friction and wear properties. Secondly, the type of the particle, whether the particle which we have used, nanoparticle which we have used, is hard in nature or it is soft in nature. If it will be hard in nature, it will not deform, it will have a rolling action. But if it will be the softer particle, it will try to deform. Like, well, we have different soft materials like your HBN, WS2, hexagonal bore nitride, tungsten disulfide, and molybdenum disulfide. These are the soft materials, and these form layer by layer structure. So the type of a particle will also govern the overall behavior of these sliding components. Then hardness index plays an important role. If the particle is hard, hardness index means the ratio of the hardness of the material as well as of the surface. So in these two figures, you can see that the hardness of both the material is same, but it is less in comparison to the particle. So you can see that the hard particle is being embedded in both these surfaces. But on the other hand, here you can see the topmost surface is harder in nature and this one is softer. So it is not embedding in the topmost surface, it is embedding in the lowermost surface only. So basically, the hardness index is an important aspect which also plays an important role, whether the material is soft or whether the material is hard, and what kind of a nanoparticle we are using, that also plays an important role. That is also an influencing factor. Then comes the particle size. Obviously, particle size and surface roughness has a correlation. More surface roughness will be there, it means more size of the particle can be accommodated. If the less surface roughness is there, there should be smaller particle size should be there. Here you can see that the size of the nanoparticles is large, whereas the surface is much more smooth. So these nanoparticles will not embed in these valleys. These will remain on the peaks, and certainly they will try to damage those peaks. So it will not give us the best properties. But if we take into consideration this one, the size of the nanoparticle is in the range of your surface roughness, certainly it will give you the good properties. So the relation of surface roughness and the particle size plays an important role in governing the friction and wear characteristics of the sliding as well as the rolling components. So coming towards the connection between the tribological applications and 3D printed materials, where these 3D printed materials are used from the tribological point of view, where there are the sliding contacts. The first example is the gears. First one is your spur gear, then bevel gear, worm wheels, sprockets. So you have the figure over here. gear which is made of some polymeric material is being used. Then we have the rollers. Knife edge roller is there, rope pulleys, guide rollers, wheel flange rollers. So grippers are also there, basically used for gripping action, because if you want to grip something, you need to have some friction in between that. If the friction will not be there, then the gripping action will not be possible. Then rack and gear transmission, you can see the image over here. There are also 3D printed materials are being used. Then plain bearings, you can see these are being used in the industries. These are the tried and tested applications from the tribological point of view of the 3D printed materials. This is another type of a bearing. Then threads and the lead screw nuts. You can see here also the 3D printed materials are being used. Then sliding plates. Then the two component parts. So basically, these are the industrial tribological applications of 3D printed materials. Although there are some biological applications also, as I told you, in dentures, uh, in natural and artificial joints, you can see that. But that aspect, I think I have seen the schedule. That aspect will be covered by the coming speakers, which will be on the day 2 or day 3. So that aspect of bio applications will be covered by the coming speakers. So coming towards the two component parts, what is this? A two component part, combines the advantages of two different materials in a single part. Because if we talk about the other 3D printing materials are usually optimized, for strength and rigidity. If you talk about that, so they are optimized for strength and rigidity without considering the tribological applications. But if you have to take into consideration the tribological application, which means if you have to take into consideration the wear and frictional behavior, so two component 3D printing is an important aspect. So two component 3D printing allows the tribo filament to be combined with other materials within a component, so that we can enhance the mechanical properties without sacrificing your wear as well as your tribological properties. So the common example we have is bell crank. You can see that we have used the two materials over here. Then we have the grippers. So you can see this black material is there, which will give, which is designed in such a way which will give the strength to this component, whereas this white material is used to give the better tribological properties. So basically what a bell crank is, it's a component for deflecting forces. It's greatly rigid. Rigidity protects the joint from interfering influences. That's why it is being used. The bearing points, these are basically the bearing points which are shown in the white color. These bearing points are smooth running, durable, and these are wear resistance. Because if the wear resistance will be more, so then the life of the component from the tribological point of view will be more. So basically, what we use is a good combination of is obtained by using carbon reinforced PET material, which has been proved to be the optimized tribological material, which is being used to prepare the or to produce the bell cranks. Secondly, we have the grippers. This one is a gripper. You know that the body of the gripper should have the different properties, whereas the gripping points should have the different properties, so that they should be able to grip the particular object properly. So the gripper's body is manufactured, it is manufactured with a fiber reinforced filament generally, and which is a flexible filament whose high coefficient of friction ensures a secure grip. You know that if you want to grip something, there should be some more friction, and if there will be less friction, what will happen? You will not be able to grip. So the gripper body has a rigidity in order to take the load of that body, and this gripping points have the maximum friction in order to grip the particular object. So these are basically the two typical examples of a two component 3D printing. And basically two component 3D printing, as I told you, is designed or is basically suited for tribological applications. Now, what are the future prospects of tribology? Before coming towards the original work, let me talk about what are the future prospects prospects of tribology and 3D printing, wherein we can talk about that there will be some tribological aspects where there can be these applications will be used. So we can talk about 3D printing coatings. Coatings are used for what? Coatings are used to improve the surface properties. So if you talk about from that aspect that we want to improve the surface properties, the coating through 3D printing technology is possible or is a viable option, but that needs to be explored. Then coming towards the 3D printing composites, but I can tell you that the composites are being used, but as far as today's concerned, there's a lot of scope of improvement in 3D printed components. So we can also work in that aspect. We can look for 3D printing composites. Then 3D printed texturing. Texturing basically is, to provide some patterns on the surfaces. And texturing plays an important role in governing the overall coefficient of friction. See, when we talk about the friction, you know that the friction is directly proportional to your load applied, but that is on a macro scale. But if you're talking about a nano scale or on a small scale, that is not true. In that case, it is basically the apparent area of contact. It is not the whole area of contact. There is a difference between the apparent area of contact and the real area of contact. Real area of contact is, if we talk about two cylinders which are in contact with each other. So if you talk about a circle, the real area of a contact will be pi r square, simply. The real area of contact, it is apparent area of contact. Apparent means which is visible to us. So that will be pi r square. But whether the complete circle is in contact with the other circle, no, it is not. There are certain points or there are certain asperities. If you take into consideration the nanoscale, the real area of contact will always be less than the apparent area of contact. If you can join your palms, and you can see that the area of real area of contact is different from the apparent of area of contact. If you talk about apparent area of contact, you can say the area of the palm is the contact area, but there are certain points where there is no contact between your fingers, between your palm. So in that case, your real area of contact is always less than the apparent area of contact. So at nanoscale, we talk about real area of contact, not apparent area of contact. So the texturing, plays an important role because it reduces the real area of contact. So less the contact area will be there at a nanoscale, less coefficient of friction and less wear of the components would be there. So coming towards the next future prospect, that is your maintenance, because we know that the impellers, there is erosive wear in case of impellers, or in case of a turbojets, you can see the vanes, gets damaged. So what we can use, we can go for maintenance by using the 3D printing technology. That is again a future prospect. We can look from that aspect. We can use some coatings to carry out the maintenance operation of the damaged impellers of the vanes, so that we can also look in that aspect from tribological point of view and from 3D printing point of view. Then metal 3D printing is a viable option, is in the field, but there is a lot of improvement which is required in case of a metal 3D printing. There are a lot of shortcomings which are to be overcome. So you can see from that the growth of the 3D printing in last 4 years, you can see it is metal 3D printing is gaining much more importance. If you compare with the previous years, you can see that the metal 3D printing had a less scope, but now the growth of the metal 3D printing is much more in comparison to the polymer 3D printing. So then coming towards the dentistry and orthopedics, in dentistry you can see that again, what is the data? The data shows us that by 2027 there will be a lot of requirement, of the metal, of the 3D printed parts. In orthopedics also there is a lot of scope wherein we can work. Talking about this, this is a gearing printed gear. It is a 3D printed gear which has already been used in a Toyota Supra in a seat steering mechanism. So this is a worn out gear. So what I told you is that as I was telling that we can have an improvement of these surfaces, or we can improve the life of this gearing mechanism by using the 3D printing coatings. If a sort of coating can be applied before the use of this kind of a gear for this particular application, that certainly will enhance the life of the system. So basically, these are basically the future prospects of tribology as well as your 3D printing. Now coming towards the work which we have done, the first we have done is we have studied the tribological behavior of FDM-based polymer nanocomposites. We have used the PETG material and we have reinforced the carbon fiber, because ultimately carbon fiber has the different characteristics. It tries to improve the frictional properties and also it tries to improve the mechanical properties. So we have used PETG as well as carbon fiber, and reinforcement has been used. So we have carried out the mechanical testing and then tribological testing and then analysis, and the conclusion has been drawn from the study. Basically, how this PETG CF carbon reinforced PETG has been obtained. We have the carbon fiber pellets and then PETG pellets. These twin screw extruder has been used to produce this CF PETG. So what were the objectives? To fabricate the carbon fiber reinforced PETG, to study the effect of carbon fiber and different parameters on the frictional characteristics, and then to carry out the surface analysis of the worn out samples. Testing conditions are there. We use different layers thickness, we use different loads, then sliding speeds, then the wear track diameter, and then the sliding distance was kept as 1500 meters. So basically, these were the coefficient of frictional graphs which were obtained for PETG under low speeds, under 100 RPM, and at different loads for PETG and carbon reinforced PETG, for different layering thicknesses, and then for high speeds also. So here you can see, if you talk about the coefficient of friction, we can see that the carbon, the addition of the carbon fiber reinforcement has, it has an overall effect of the effect on the coefficient of friction, which is reduced. If you see this carbon reinforced PETG over here, and if you compare it with, you can see that the coefficient of friction in that case is mostly less in comparison to this one. Basically, this is basically due to the intrinsic nature of the carbon, that is, as I told you, that it acts as a self-lubricating material. The carbon reinforcements, basically what it does, it adds strength to the polymer matrix. The real area of contact with the counter body under load is reduced. As I told you, what is the apparent area of contact and the real area of contact. So real area of contact has an important role to play in tribological applications. So due to the reduction in this true contact area, the layer thickness did not affect the coefficient of friction at different loads for carbon reinforced PETG. Also, as I told you, the film formation capability that basically I will tell you in your SEM analysis, which we have carried out in the coming slides. So the film formation capability of the carbon fiber further aided in reduction of the coefficient of friction even at these high speeds. So if you talk about the effect of load, you can see that there will be an increase in the coefficient of friction with the increase in the load. If you'll see over here, there is an increase in the coefficient of friction. There is also a slight increase leading this result. So there is also an increase in the coefficient of friction, which is, as per the basic laws of friction. With the increase in the load, there will always be an increase in the coefficient of friction. And if you talk about the effect of speed, because these results are at the left side, results are at the low speeds, and these are at the high speeds. So it can be seen that at low speeds the coefficient of friction is lower than at the high speeds. Coefficient of friction over here is less in comparison to over here for both the reinforced and unreinforced PETG. So these results are basically due to the increase of adhesion at the high speeds. Basically, as I told you, that what adhesion is basically the binding of the two surfaces with each other, two sliding surfaces with each other. So what happens is that at high speed, what happens, there is a possible increase in the temperature, and due to the increase in temperature, the chances of adhesion are increased. So coming towards the frictional characteristics, how the friction is behaving, you can see that the friction behavior has been shown for PETG and CF PETG at 100 RPM and 300 30 Newton load. So it has been shown over here. So you can here see that for PETG, which is not reinforced with the carbon fiber, there is an increase in the coefficient of friction with the increase in the number of cycles. There is at the start the coefficient of friction was less, but it is increasing, and certainly there is a sharp peak which can also be observed for a particular layer thickness. But in comparison to this figure here, you can see that the coefficient of friction is quite stable and it is decreasing. And here you can see that the coefficient of friction has not crossed 0.2, but here the coefficient of friction has crossed 0.2 in for these two layer thickness values. So certainly, as I told you that the carbon fiber reinforced PETG has the better frictional characteristics in comparison to the PETG which is unreinforced. So similar case study has been done at the high speeds. Here you can see again there is an increase, and the coefficient of friction here you can see it is 0.2 and 0.3 is in the range of that. But here the carbon reinforced PETG has shown less coefficient of friction, and the behavior of this these curves is quite good in comparison to this one. The curves over here are staggered, but the curves is, over here is smooth. And in these two cases, you can see that the coefficient of friction is basically decreasing with the increase in number of cycles, and that basically should be the requirement of a particular material from the tribological point of view. So these are the surface analysis which have been obtained after carrying out the SEM analysis. You can see that this is a we have obtained these SEM analysis for grid PETG also and grid CF PETG. You can see that here the delamination is there. Surface after sliding contact is you can see the surfaces over here is the damaged portion over there. The plastic deformation is always also there. The grooves are also there. So there is a lot of damage on the surface in comparison to the surface which is reinforced with carbon fiber. Here the surface is much more smooth in comparison to this. This SEM has been carried out at 200 micrometers. So if you take into consideration the triangular PETG, here also you can see there is a lot of deformation which has taken place. But whereas if you talk about carbon reinforced PETG, you can see again the surface is smooth. So similar case kind of observation has also been made with the honeycomb CF PETG. So in short, what we can say is that carbon reinforced PETG has the capability to reduce the frictional characteristics, to reduce the wear characteristics, and ultimately to give the smooth surface finish, which is ultimately the requirement of any sliding component from the tribological point of view. So we can use carbon fiber PETG in the applications, in the 3D printing applications where where we have the sliding contacts, where we have the rolling contacts. So coming towards the conclusion of this particular study, not about the complete studies. So for this particular study, you can see the tests were carried out at different loads and different speeds. So what was observed? The carbon fiber increased the strength of the polymer, although the mechanical testing has also been carried out, that I have not shown over here because the objective was to show the relation between the tribological characteristics and the 3D printing. So mechanical strength or the mechanical studies have not been shown over here, only tribological part has been shown. So carbon fiber increased the strength of the polymer and its intrinsic lubricating nature, which sorry. So carbon fiber increased the strength, and also it improved the frictional resistance. The coefficient of friction was reduced by 47% at 100 RPM for a particular layer thickness, that is 0.0 mm, and 44% at 500 RPM for 0.18 mm layer thickness. So the analysis which have been shown in the previous slide, it was observed that there was a different wear mechanism. At some places there was some adhesion, at some places there was some abrasion. So that also resulted that the role of CF in smoothing the surfaces is quite visible in the scanning electron microscopic images which have been shown in the previous slide. So coming towards the next study, which has been carried out by again my group. In This is regarding the surface engineering of FDM based 3D printed parts. In that, as I told you, that the texturing is also playing an important role. So in that case, we have tried to explore the effect of texturing on the friction and wear characteristics, because as I told you, the contact area again plays an important role. And further, if you're talking about the lubrication, then these textures have the lubrication retention capability, and due to which what will happen, there will be less coefficient of friction in comparison to the dry states. So we also tried to explore the lubrication retention capability of these textures um, in the second part of the study. So what was the objective? We basically produced three types of textures to create the textures of different sizes using FDM. Then we studied the effect of surface texture size on the friction behavior under dry and lubricated conditions. Then again, this effect was studied for high speeds and low speeds. And then the scanning electron microscopic analysis were carried out. So what was the process? Here we have used PLA, not the other materials. So we selected the waste material, then printed, then various frictional parameters were selected. The sliding distance is an important parameter, load, velocity, type of texturing is also an important parameter, and density of your texturing, how dense the textures are, that is also an important parameter. So based upon all these five parameters, we carried out the testing, and then the surfaces were analyzed for this purpose. So the frictional characteristics under dry sliding conditions, you can see under dry sliding conditions, and first at the low speeds, you can see we have the pins likewise this, and this is a uh, zoomed view of the pin which is shown over here, and you can see the textures over here. We generated these textures on those pin surfaces, and we try to study the frictional characteristics, effect of load on CUF, and we try to analyze the surface uh, analysis. So this figure basically, this figure, it is regarding your frictional characteristics. It gives the variation of coefficient of friction with the number of cycles at 30 Newton load and 100 RPM under dry conditions. So for texture T1, you can see this here. We have for the texture T1, the coefficient of friction increases linearly up to 1100 cycles. You can see the text for texture T1, the coefficient of increase up to 100 cycles, 1100 cycles. For this time, this one. So for the texture 2, the coefficient of friction is high at the start. This texture, red one texture is there. The red curve is showing that the coefficient of friction is basically it is high in comparison to the other textures at the start. So, but you know, after a few cycles, it decreases. This may be due to more interaction of the asperities at the start. Certainly, what happens is that at the uh, start or at in the running in condition, what's there is the interaction of the asperities, and the interaction of asperities basically causes adhesion, and due to adhesion, what happens is that there is more resistance, and which leads to an increase in the coefficient of the friction. But after some time, when the running, when the steady state condition is improved, achieved, the coefficient of friction curve basically tends to stabilize. So after some cycles, there may be a formation of transfer film due to entrapment of the soft particles. Basically, PLA is a soft material, and the particles, you know, which are worn out from that surface, that can, you know, that can be entrapped, and that may have, you know, help in the formation of a smooth film. So that's if there is a smooth film between the sliding components, that ultimately will reduce the coefficient of friction, and that certainly it will reduce the resistance which is being caused due to the sliding. So for texture 3 T3, which is again shown over here, this one. So for texture T3, the coefficient of friction increases till 1000 number of cycles, and then it tends to stabilize. Also, there is no abrupt breakup. There is no generally there if there is an abrupt peak, which is in the case of black, this one, and it certainly means that there is some resistance which has been occurred due to some foreign particles or due to some wear debris. But in the texture T3, there is no abrupt peak, and then after after this time, after 11 or 10,000 number of 1,000 number of cycles, you can see there is not much change in the coefficient of friction. It is somewhat in a stable range. So what is all about? These are the friction characteristics. So this result is plotted over here, because we cannot show the graph of all the results. We have shown the results, frictional behavior of different textures at load 30 Newton. So this 30 Newton load has been shown over here. You can see these are the results of the coefficient of friction in this case. So similarly, we have also obtained the effect of load in each and every case. At 10 Newton load, 20 Newton, 30 is shown over here, 40 and 50. So from these figures, you can see that the texture T2 has a less coefficient of friction in comparison to the texture T1 and texture T3. So these are the results. Basically, we try to find out the optimum texture size or the optimum texture density, which will give us a minimum coefficient of friction, which is possible with the texture T2. Because the size of the texture T1 is, it is less. Size of the texture T2 is more, whereas the size of texture T3 is much more. So if you come or take into consideration the SAM analysis in all the three cases, again at this load, so you'll feel this corresponds to this one, this second curve corresponds to this one, and this one corresponds to this one. So here you can also see that for texture T1, there is again some parallel roofs, which you can see. Again, parallel roofs means that there is some kind of abrasion is there, some kind of material removal is there, and some plastic deformation can also be seen over here. The surface is not smooth in comparison to this one, which is for the texture 2. The surface is smooth over here, and certainly for texture T3, again the surface is not smooth. So certainly it indicates that there is less resistance, which has been caused due to sliding and due to during the tribological testing. So this texture T2 has resulted in good properties or minimum frictional properties in comparison to the texture T1 and texture T3. Now coming towards the frictional characteristics under dry sliding conditions, but these are at the high speeds. So the high speed characteristics, if you take into consideration, you can again see the frictional characteristics over here. Texture T1 has shown varied behavior, whereas the texture T2 has also shown some different behavior. At the start, the coefficient of friction is high, but it certainly decreases after steady state, after 200 number of cycles, and tries to stable out. Whereas the texture T3, the coefficient of friction increases, and then the coefficient of friction is more in comparison to the previous cases. So if you take into consideration all these coefficient of frictions at different loads, again texture T2 has proved to be a good texture, which has resulted in the minimum coefficient of friction. But the surface damage is comparatively different from the previous case. This is basically due to the high speeds. More speed will be there, more heating will be there, and due to more heating there will be more adhesion. And what will happen if the adhesion will be there? It will the surface will the adhesive wear will be more, and the surfaces will be damaged more in comparison to the previous cases, as you can see from these previous figures. So, but if you compare all these figures, you can see the surface damage with the texture T2 is comparatively less in comparison to the texture T1 and T3. In texture T1 and T3, you can see there is a lot of plastic deformation, and the surfaces are, the material removal in this case is much more in comparison to the texture T2. Then under lubricated conditions, the testing was also carried out, but the principle and the behavior is different for the lubricated conditions. In that case, we have used an oil, and you can see the curves are much more smooth in comparison to the previous dry cases, whereas we have this is for low speeds, 100 rpm. These results are for high speeds. You can see that the curves are stable, and the coefficient of friction decreases with the decrease in the number of cycles. And here you can see that the texture T3 has proved to be a minimum, has given us a minimum coefficient of friction. Certainly, that is quite logical, because if you take into consideration the texture size of the T3 is more, and if the size of the texture is more, they have the more oil retention capability. and if the oil will be more in during the sliding operation, certainly the friction will be less. So which is quite justifiable in case of your low speeds, which is 100 rpm, which is very low speed. So that's why the T3 texture has shown minimum coefficient of friction in comparison to the other textures T1 and T2. Whereas if you talk about the high speeds, the reverse case is the texture T1 has shown the less coefficient of friction in comparison to the texture T3. The reason here again is quite logical, because if you increase the speed of testing, 100 rpm was the low speed and 500 rpm was the high speed. So what will happen? In that case, what will happen? Your the oil will not be retained. Basically, we are talking about the lubricant retention capability. If the speed is less, the lubricant will be retained. If the speed is more, the lubricant will be tried to get away from the textures due to the centrifugal action. You can see the tests have been the tests have been performed on a pin-on disc rotating machine. So whenever there will be a rotation at a high speed, there are some forces which try to throw the lubricant away from the surface. So in case of a texture T1, which is smaller in size, it has more lubrication retention capability than in the texture which is has much more size, that is T3. So here the lubrication retention capability of the texture T1 is more, but here the lubrication retention capability of the T3 is more. So we can select the texture depending upon the type of the requirements for which we are using these materials, and we can optimize as per our, or we can customize the parameters or the properties as per our requirements. So if you take into consideration the comparison at the high speeds and the low speeds for dry condition testing, and for the high speed and low speed, dry versus wet, LT1 means lubricated texture T1 with respect to dry texture T1. So here in all the cases you will see that the lubricated texture has improved the coefficient of friction nearly by 80 to 90%. Lubrication texture T3 with respect to dry texture T3, this one is the curve. So this has improved the coefficient of friction nearly by 80 to 90%. So which certainly means that the lubrication and the oil retention capability of the texture T3 has resulted in your reduced coefficient of friction. Similar kind of results are also obtained at the higher speeds. So under dry sliding conditions, the coefficient of friction was minimum for texture T2 at both high speeds and low speeds as obtained. But under lubricated conditions, at low speeds, T3 has the least coefficient of friction as told to you. The texture T3 has a bigger size, has lubrication capabilities more, as has been discussed previously. But whereas in case of high speeds, the texture T1, the coefficient of friction was minimum for the texture T1. This is due to the difficulty of trapping the lubricant. Again, the lubrication retention capability was less, which prevented the effective lubrication for the large size textures. And the surface analysis carried out for dry testing and showed that wear is mainly due to adhesion and abrasion. You can see that the wear was mainly due to the flowing effect in all those SEM images which have been shown to you. And again, the comparison which was carried out for dry and lubricated conditions revealed that the lubrication conditions have a substantial effect on reducing the coefficient of friction in all these cases. So this was a small study which is again in process. We have not completed this study related to the erosive wear. So we have tried to develop some impellers in that case by using 3D printing technology, and the performance parameters we are trying to obtain, that is your discharge, output power, input power of the pump, and then efficiency of your pumps. So this study is still in process. I'll show you what we have done till now and what is still to be done. So we have obtained 3D printed impellers. We are trying to carry out the real-time testing for these 3D printed impellers. We have printed these impellers, and we will try to check the erosive wear characteristics. And in order to check the erosive wear characteristics, we will use the different fluids. So what we have done till now is we have obtained all these 3D printed impellers, and we have used the 3D printed impeller in a small pump, And again, we have carried out some testing with water itself, not with the different fluids. And we are in the process of, to carry out the erosive wear of these 3D printed impellers, which have been printed by your PLA. So this is basically all about the tribology and 3D printing applications, because since we know that wherever we are talking about material development, because 3D printing is a material development technique, there is always an area where you should look into consideration or take into consideration the moving and the sliding components. And if you're talking about moving and sliding components, then certainly tribology comes into there. So if you're talking about the 3D printing, so that should also encompass the tribological applications and the tribological properties of the materials which are being developed for particular applications. So these are basically the acknowledgements. My colleague, my Dr. Mir Irfan Ulhaq, whose talk is, I think, in the morning, tomorrow morning. He's working with me, assistant professor as a video. Some part of the studies will be shown by him also. He'll talk about, I think, mechanical aspects which I have not taken into consideration. Then Miss Aisha was our MTech student. She has carried out some work. Miss Rutba, she has also carried out some work. Then the last part of the work which is being carried out by our BTech students regarding the impellers, that is Aryaman Singh, Wazir and his group. And finally, some special thanks to the in charge 3D printing lab, Dr. Ankush Ram, who is an associate professor over here in SNVDU. So I thank you very much. If you have the questions and the queries, you can please ask me. Let me check whether.
Thank you, sir. Thank you so much. Now, I would like to take pride in saying that the knowledge gained in this session gives us confidence in our study. Today's sir lecture help us to understand the concept of tri-biological application in 3D printing parts in detail, including basic concepts like additive and subjective manufacturing, 3D printing and its prototype, their techniques, material, and their challenges, and so on. And special topics like biological and its application, type of wear, lubrication, future prospects, and their behavior. Thank you, sir, for putting your effort, heart, and soul into your lecture. Your lecture had a significant impact on every participant present in this virtual classroom. We are heartily thankful to you to share your precious time from your busy schedule. So, participants, the next session will start at 12 p.m.
Thank you,
Any
Dr.
query?
Renu. Thank you very much.
Yes.
If any participant having any query, then ask to the sir.
Ma'am, there is a one query for Ankush sir.
Okay.
Can we customize the raw material used for additive manufacturing? It is by Manoj Singla.
Yes, sure. We can customize the raw materials also based upon the properties which are required, or based upon the applications where it is to be used. Then only we can 3D print, because fiber reinforced and nanoparticles reinforced these raw materials will be these finished materials will be obtained by customizing the raw material only. So we can embed the nanoparticles, we can embed the nanofibers in the raw materials, and then we can use those materials for additive manufacturing. So we can do that. That should be done rather, because after that it may not be possible to produce the composites or to produce the parts which will be subjected to some particular applications. So we can do that.
Okay.
Yes,
Thank
any
you.
other query invited? Thank you, sir. Thank you so much for this wonderful session.
Thank you, Dr. Renu. Thank you very much.
Thank you.
And I am also thankful to the organizers, particularly Dr. Deepak. Thank you very much, sir. Have a nice day.
Okay. Thank you, sir.
So can I leave?
Yes, yes.
Yes, sir.
Okay.
Yes.
Okay. Thank you very much.
The next session will start at 12 o'clock.
Now